All right, this is the fourth installment of the practice final for quarter 2 in college algebra. And the scene we're looking at now is scene 4. And in this scene, there's this little element called Chuck Norrisidium. It's very radioactive, and it has a very, very, very long half-life, which means it sticks around for a very long time. So that's not a good thing. When you have radioactive material, you'd like half-lives to be really short, so that if you have exposure to it, then it decays rather quickly and isn't exposing you over a long period of time. So anyhow, the big important stuff that we want to take out of this is actually the following numbers. And we want to find the initial amount. Okay, so somewhere you'll have an initial amount. So that's 5 grams. You want to find the decay rate, the half-life. Okay, 16 million years in this case. And we also want to know what the end amount is going to be. So that in this case is 1 gram. And you just get that from the reading. In the real final, it should be pretty obvious. I tried to take out a lot of the extraneous words, so it'd be a little easier for you to find what you needed to find. The equation we need to use is this puppy right here. And the way we match it up is that this is the initial amount. So in this case, that was 5 grams. The final amount is going to be the amount at time t, and that's 1 gram. So the final amount. And then we have the time and the half-life. We're actually going to be solving for t, okay, which is how long would it take to decay from the initial amount to the final amount, given a half-life of 16 million years. 1, 2, 3, 4, 5, 6. 16 million years. Okay, so I'm going to go ahead and write this out nicer over on my evidence sheet. And I've got the initial amount, P naught, is 5 grams. The final amount, PT, is 1 gram. The half-life is 16 million years. And we want to find t. All right, so we have to do a little bit of logarithmic manipulation here to get t by itself because it's in an exponent. And we know the way to get rid of exponents is to take logs. So pt equals p naught times 1/2 raised to the t over h. So first thing I want to do is I want to try and isolate t. And I'm going to do that by getting things unstuck from it that are currently stuck to it. So working my way outside, I've got this p naught. I can get rid of that by dividing both sides by p naught. Okay, and that'll take me so that I have now pt over p naught equals 1/2 raised to the t over h. Now, I want to take the log of both sides, and I like to use the natural log just because it's one less letter. And I take the natural log of both sides, and the reason I do that is because I want to be able to swing this exponent down to the front. So let's rewrite that as ln, stick with my color schema, ln of pt over PO equals T over H times ln of 1/2. So I'm almost there, almost got T by itself. If we now divide both sides by the natural log of 1/2, ln of 1/2, ln of 1/2, that'll give us, so that we're almost there. In fact, I'm going to go ahead and combine that last step here because I know that that'll leave me with an h that needs to be multiplied by both sides so that I get t by itself. So I'm going to go ahead and rewrite that in its final version as h times natural log of pt over po all over the natural log of 1/2 equals t. So now we can plug and chug. The half-life was 16 million years. Multiply that by the natural log of the final amount divided by the initial amount over the natural log of 1/2 equals t. All right, let's put this into Desmos and see what we get. All right, so 16 million, 1, 2, 3, 4, 5, 6, all right, times the natural log of 1/5. And then I'm going to end that parenthesis. Whoops, we need to move it out 1. And now end the parentheses. I'm going to divide that by the natural log of 1/2. We could have cleaned all of this up, you know, using our log rules and whatnot to make it so it's a little prettier to enter. But since we're just getting an answer that's in an actual number form, it's just not that important. All right, I've got an extra parentheses in there. But there we go. Okay, and that should be it. And I have, let's see, t equals 37150,849.5. All right, now remember, these are years. It takes 16 million years for it to degrade halfway. All right, so it's going to take more than 16 million years. Right, so it would have taken 16 million years to go from 5 to 2.5, and then so 16 mil. 2.5 to 1.25 grams would take another 16 mil. Right, and then we're somewhere in between there because we want it to stop right at 1 gram. So it makes sense that it's going to be between 32 million and 46 million and closer to the 32 because 1.25 to 1. All right, the decay is not linear. So this answer, even though it's really big, makes sense to me. So there we go. Our clue is going to come from, let's give this back over here. All right, 37,150,850. That looks right to me. So our clue is I, and it's 37150,850. Excellent. It's nice when they have an answer right there for you to make sure that you got it right. All right, so same game for you guys when you are doing your radioactive decay problem. It will be doing with radon, and so have some fun with that. And next installment, we'll look at clue